All right, guys. Second day out. We have an X day. So for X day, I wanted to push you guys a little bit further along here, and that means we're gonna have to learn something a little bit new. So no big deal there. Ultimately, what I wanted to stress today is electrical power, which I referenced in the other video is P equals I times V. The power is the current times the potential difference, which we call voltage, right? And the units for power are then going to be watts. Watts are the amps times the volts. These are the units, okay? All right, and it's a capital W for watts. So that's laying things out. So here's a scenario. You're at home, you're doing WebAssign, and you have a few devices on. I probably haven't even listed all of the devices you guys have on when you're working on homework. And all of my devices are at home, which you might not be when you do your homework. So you happen to have, in this case, your 120 watt laptop, like the charging brick is basically plugged in with your laptop charging, a 75 watt light bulb in your lamp. You're listening to tunes on obviously an 80s style 200 watt boombox. That's what it looks like in my head. And your cell phone is charging with a 5 watt wall charger. Okay, all of these devices are wired in parallel. Don't worry about that so much now. We're going to talk a lot more about that later. We want to kind of get the basics of the main two formulas, which is V equals IR, Ohm's law, and then their power relationship with current and voltage. And beautifully, we can actually plug in one of these formulas into the other and do some things like if I plugged V, voltage, which is really I times R, in for the V that's over here, well then I'm going to have I times R, so I squared times R. And we'll get to work with those like extra equations a little bit later. They just speed things up in certain problems so you can do them in one step rather than two. So just a heads up. All right, so the first thing is, what's the circuit look like? All right, so any home circuit, first of all, any circuit has to have a positive and a negative, and you got to make a loop. You have to make a circuit. So coming out from your circuit panel, you have a wire, then you have a circuit breaker. Your circuit breaker, if you read on in the question, it says all of the devices are in parallel, and the entire circuit is protected by a 30 amp circuit breaker. A circuit breaker acts like a switch, so it just sits there and it just waits until the current peaks above 30. When that happens, it goes from being a closed switch and it pops open and becomes an open switch if the current peaks above 30 amps. It takes you 0.75 hours to complete your homework assignment. Web assigns every week for the entire 9 months that we are in school. PICO charges your parents 12 cents per kilowatt hour. We will talk about a kilowatt hour and what that means. Essentially, there's a good deal of unit conversion that happens in this problem. Oh, you know what? I wanted to ask question G, which is how much does WebAssign cost your parents for the year? Okay. All right, so here's our positive, and we have 110 volt supply. Comes out, it comes back around. If nothing's on it, that's your whole circuit. It's actually not completed at that point because nothing's been plugged in across this section here. So essentially, your wires in your house at the outlet look like this at the outlet. And they're just waiting for things to be plugged in, attached, and connect the two sides of the circuit so that it can start using some power. And so that's what you do when you plug something in. So here's your first thing. Your laptop gets plugged in. It's 120 watts of power. Now we got another thing that's plugged in. That's your light bulb and your boom box. And finally, your wall charger. All right, So this is what the circuit looks like. This is what parallel means, by the way. The resistors, all of these power using devices, we call them loads, are all lined up parallel to each other and using up the power like this. Again, we will talk about how that's different than what's called a series circuit next week. So current flows out of the positive. That's always the way it goes. It flows out of the positive. It goes across each one of these. Obviously, it has to continue down here, right? Not all of it. Some of it continues down. Some of it comes across here. Some more of it splits off here and splits off here and splits off here. And then eventually it all comes back this way. All right, so going into and out of the supply, the wall essentially, the circuit breaker panel, we have only to be concerned with that for now. We have some power coming out and it comes back in. Okay? Are you kidding me? Sorry, guys. $75 watts, 200. Oh. All right, that should be back to how the diagram was. Okay, so how much power are you consuming? Well, that's literally, in any question, as easy as adding the powers up. So we have 120 watts, and 75 more, and 200 more, and 5. So the 75 and 5 makes 80, 80 and 120 makes 200. So total, when you add in that other 200, you're using 400 watts total. So that's the answer to B. What is the current through the whole circuit? Well, we've got a nice equation for that. Power in the whole circuit is equal to the current in the whole circuit times the voltage of the whole circuit. So the voltage of the whole circuit, or the potential difference, is the 110 volts. The power we just figured out is 400 watts. All right, when I divide the 400 by the 110, I get that the current in the entire circuit is going to be equal to 3.64 amps. All right, you just type in 400 over 110, you get the same thing. Okay, so this is B, this is C. So now let's go to D. Will the circuit breaker be able to handle this amount? Well, the current that I need to use with all these devices is 3.64 amps. The breaker won't open up until 30 amps. So will the circuit be able to handle this? Absolutely. So this circuit breaker will remain closed. It will not pop open because the 30 amp maximum has not been reached. What must the overall resistance of the circuit be? Okay, here's where we start to cycle back now. You know V for the circuit. Oh, by the way, the 3.64 amps. That's what 3.64 amps here and here. That's coming out of and going back to the supply. There are two things called loop rules, which I'm going to talk about in a moment. Well, actually, there's two rules. They're called Kirchhoff's rules. All right, Kirchhoff's rules. And he has two rules. One's called a loop rule, and one's called a junction rule. I'm going to explain those in a minute here. We'll come back and circle back. All right. So for now, right, what must the overall resistance be? So I know, and you're going to use this equation so many times. I always know, and I'm keeping it in the back of my head, that I know this. V equals, it's a law. V equals I times R. So the voltage for the whole circuit is equal to the current for the whole circuit times the resistance. So if I divide under by 3.64, I find that the resistance of the circuit, the entire thing, is going to be equal to 30.22 ohms. Now what that means is, remember, I'm using the total current, the total power, the total voltage, right? So basically what I've done when I do this is create what's called an equivalent resistance. That's what this is. And what that means is R is not R, the resistance of any one of these devices. It's the resistance of all four of those devices acting as one. For example, a circuit that looks like this. Here's my 110 volt source. I come out. I go across my circuit breaker. And then I hit one resistor equal to 30.22 amps. Is that really what's going on in the circuit? No. But I'm acting as though all of the resistance values up there, all four of those items, act as one individual item. Well, wait a second. 120 plus 75 plus 200 plus 5, that doesn't add to 30.22. Whoa, I wrote amps. Sorry. That's a problem. Should be ohms, right? Well, these are not resistance values. These are power values, and this is a resistance value. All right, we found resistance. Even so, when you add resistors in what's called parallel, we're not going to find out that you just add them up anyway. Not in parallel. There's another type of circuit called series where you do. And so we're going to go all into this next week. However, we still have enough info to be able to figure out these individual circuit loads to figure out their individual resistance values. So the overall resistance of the circuit is there. What are the resistance values for each device? Well, I mean, look at each device. Let's look at the first one. 120 watts. It's 120 watts. Now, here's where the loop rules come in. Kirchhoff's loop rule says for any loop in a circuit, all voltage from supply must be used. All right, so let's show the first loop. I started 110 volts. This is basically cutting out the first loop made, right? Electricity comes across and loops and finds a path back to the zero because of that potential difference. So loop rule, any loop, all voltage from the supply must be used. Well, how much voltage is going to get used in this loop? 110 volts. Well, look at that. Power, voltage, P equals IV. P equals IV, I know that, right? 120 watts I times 110 volts. I can divide there and find out, right? 120 over 110 is 1. We're going to call this current number 1, is 1.091 amps. Okay, that's the first loop. Let's look at the second loop. The second loop is going to go out of the supply. I'm in the top left corner. Out of the supply, over the 75 watt, and all the way back to the zero. All right, if it can avoid resistors, it will. So if I look at this second separate loop, the only resistor it's going to pass to make a loop back is the 75. Electricity never comes out, goes to the 75, comes back around to the 120, because after it exits the 75, the fastest path is back to zero. All right, our fastest path back to zero is that straight shot down and around. All right, so we would do the same thing for the for each of the other resistors. So we're going to have power of resistor 2, 75 watts, is I2 times the voltage. And again, that circuit is going to look just like the other one. It's going to look like 110 volt supply, a resistor, and back, 0. And so we're going to have P is I2 times 110 volts. And so I2 is then equal to 0.682 amps. So I've got one current, two currents. I have three. Wait a second, the currents are splitting. That's the second rule. The second rule is called the junction rule. And it'll make a lot more sense in a second, so I'm not even going to write out the rule yet. Let's figure out the other two currents. So again, P3 is the, up here, 200 watt supply, or 200 watt power. So that's your, well, what was 200? The boombox times current 3 times the voltage again. Again, the loop is just going to look like, boop, 110, 0, 200 watts. Oh, not negative, just 0. So 200 watts, I3, 110. And so we find that I3 is 1.818 amps. And finally, P4, 110 volts. I don't know I4. Power 4 is the 5 watt charger. I4 is 0.0455 amps. So I had 4 currents, right? Well, the junction rule says at any junction, which is what starts to happen here, but that's part of the junction, that's part of the junction, that's part of the junction, that's part of the junction. A junction is where current splits up. So the current splits up 4 ways. Any junction says at a node, that's like an intersection of wires, that when at that junction, any current that comes in needs to be equal to the current that comes out. 3.64 needs to be equal to 3.64, which means down all of these individual I1, I2, I3, I4 paths, they better all add up to I total. So if we add I1, I2, I3, and I4, I find that I total excuse me, I find that I total is 3.64 amps, just like I found out way earlier in section C. And I'm just proving that all of that current comes back together, right? Now this particular one wants us to find what? What are the resistance values for each device? Okay, so, resistance. You know how to do that. Because we know 2 things that are super important here. We know V and we know I, voltage and current for each of the resistors. So for resistor number 1, V equals I times R. And just to remind you, that's resistor 1. That's the 120 watts. That's your laptop. So what do we know about the laptop? Well, it had 110 volts across it. It had a current that we just figured out earlier, I1, which is 1.091 amps. And so R comes out to 100.8 ohms. And we do the same thing for R2. R2 is going to be 110 volts. Let's separate this word. Is I2, which is, right, I2 is the 0.682. I get 161.3. This is R2, R1. Oh. Same thing for R3, 110 volts is equal, whoops, should have been times R2 earlier. So this is V equals I times R. That's all I'm doing every time here. 110 volts is equal to I3, 1.818 amps times R. I get 60.5 ohms. And then lastly, R4. That was the really small current. Times R. Whoa. 2,417.6 ohms. 2,417.6 ohms. Right, so we found all the resistance values, and lastly, the very last question is about cost. Cost. How much does WebAssign cost for the year? Okay, so this one can be a little different. This is G. By the way, all of this that we just found out of R1, this is all tedious. This is called circuit analysis. You're not going to be asked to do this in the WebAssign, but this is where we're headed, so I wanted to at least show you. So all this, that's a star. All this, finding out each of the I values, all of the R values, all of that is called circuit analysis. That's where we're headed, and so I just wanted to give you a preview, okay? That's kind of, I walked you through that. You're not going to be expected to do that part on the website. You're going to be focused more on parts A through, what? A through D. And then you will be asked about G, which is the cost, okay? So here's what we want to know is how much does WebAssign cost for the year? Well, you know that you use a total power of 400 watts, right? 400 watts. You know, so that's your power. We're eventually looking for a dollar amount. How much does it cost? Price. And we're going to take the power, but we don't like this, the watts, and I'll show you why. We're going to take the power, and we're going to take the cost of the electricity, and we're going to times that by how much time it operated for. So the cost is an interesting unit that they give you. They tell you how much you pay in $1.12 per kilowatt, watt. That's why I don't like the watt. I gotta change it into kilo. But kilowatt, not kilowatts per hour, kilowatt hours. That's actually an energy unit because power times time. In the last video, power was energy over time. That was like the old power we did before when we worried about horsepower. So power times time equals the energy. Okay, so that's an energy unit the companies use, so that's why it's kilowatt hours. All right, so this is going to be nice because I'm going to cross out watts, but I'm going to have hours here, and I want to have dollars for the price as my answer, right? I need to have a dollar answer for how much WebAssign costs my parents. So I need to convert my time into hours for this to cancel. So I have to figure out what that time is. So for your particular homework assignments, it says what? Let's see. For a full 9 months, and I'm assuming 4 weeks in a month, by the way, you do 2 WebAssigns every week. They each take 3/4 of an hour, and you do this for 9 months. So 2 WebAssigns every week, and you're going to do it for 9 months. 9 months is the same as saying what? 32 weeks? Okay, so let's see how many hours you're actually spending, right? So there are, this is all to figure out the time number, and we need it to be in hours. So you have 32 weeks in a year. And by the way, this price is going to be dollars per year, right? Isn't that what I asked? How much do you pay, does WebAssign cost your parents for the whole year? 32 watts per year. 32 weeks. per year. Okay, well, we said that there are, what, 2 WebAssigns a week, per week, and each one WebAssign is 0.75 hours. So my units here, WebAssigns, weeks, I'm going to have hours per year, which is what I want. I wanted to get rid of hours and introduce years on the bottom. All right, so if you multiply that through, you should find out, at least what I found out, that you spend 48 total hours in a year working on WebAssign. So that's the time, 48 hours. Hours cancels. I don't like 400 watts. 400 watts, 1,000 watts is a kilowatt. So this is going to come out to 0.4 kilowatts. 0.4 is going to actually go in here. Oh, geez. Technology. Kilowatts is going to be up top, actually. It's this number up here. Right? We just got rid of it. That's going to cancel this. And so I'm going to be left with 0.4 times the 48 hours times the cost of 12 cents an hour. And I'm going to find that WebAssign only cost my parents a whopping $2.30 per year.